Oke, aku share screen. Oke, udah terlihat ya. Baik, selamat malam semuanya. Hari ini kita akan belajar di minggu ke-9. Kita hari ini belajar tentang device-based model in TensorFlow Lite. Materi hari ini cukup berat, karena nanti kita juga lihat pembuatannya di Android seperti itu ya. Tapi nggak akan kita bahas terlalu dalam untuk Android-nya. Kita hanya membahas tentang TF Lite-nya untuk di Android. Seperti itu. Oke, kita lanjut. Nah, agenda hari ini kita akan belajar tentang dua hal, yaitu training on model, dan yang kedua running TensorFlow model in Android apps. Objektif pembelajaran hari ini yaitu yang pertama mengerti cara kerja TensorFlow Lite, yang kedua memahami apa itu model quantization, yang ketiga dapat menjelaskan cara kerja GPU delegate, dan yang keempat mengenal optimization teknik bagi TensorFlow Lite. Oke, apakah udah siap semua? Jadi hari ini cukup panjang. Oke, ready ya. Hari ini cukup panjang sama lumayan berat materinya. Oke, kita next. Recap. Masih ingat nggak nih, kemarin kita belajar tentang apa minggu ke-8? Kita belajar tentang dua hal minggu ke-8. Boleh ditaruhin di kolom chat. Kira-kira minggu ke-8 kemarin kita belajar tentang apa aja nih? Structuring Machine Learning dan TensorFlow JS. Ya, betul ya. Minggu kemarin kita belajar Structuring Machine Learning dan TensorFlow JS. Di minggu ini kita juga akan belajar dua hal. Yang pertama, Device-Based Model in TensorFlow Lite. Dan nanti di hari ketiga kita akan belajar Data Pipeline. Di hari Jumat. Oke, kita next, kita lanjut. Nah, part yang pertama hari ini kita belajar machine learning model in mobile and embedded system. Oke, fiturnya lightweight, low latency, privacy, improve power consumption, lalu efficient model format, pre-trained model. Oke. Nah, komponen di TensorFlow Lite itu ada dua, converter dan interpreter. Untuk yang converter itu TensorFlow Lite format. Jadi dia mengubah model TensorFlow dalam bentuk yang lebih efisien dibaca oleh interpreter. Yang kedua, memperkenalkan optimization untuk meningkatkan kinerja model dan atau untuk mengurangi size model. Nah, interpreter atau core itu ada support multiple platform, itu Android, iOS, embedded Linux, microcontroller. Hari ini kita bahas banyak yang Android. Terus yang selanjutnya, platform API for accelerate inference. Nah, ini arsitektur dari TensorFlow model, ini TensorFlow Lite. TensorFlow model, terus memiliki converter, dia ada Android, iOS, Linux. Nah, kalau yang Android itu ada Java, C++, API. Ini juga ada Kotlin ya, kalau Android itu pakai bundle-nya Kotlin. Ada iOS, Shift, atau CIPI. Linux itu Raspberry Pi or Coral, Python, Java, C++, IPI. Oke, ini performance. Performance-nya ini acceleration-nya software sama hardware, available-nya NNIPI, HTPU, GPU, CPU optimization. Nah, ini ada also delegate. Nanti kita bahas tentang delegate juga. Jadi performance ini untuk biar lebih optimisasi gitu ya, optimization. Nah, tadi ada NNIPI nih di available. Nah, NNIPI itu Android Neural Network API. Adalah Android CIPI yang dirancang untuk menjalankan operasi komputasi intensif bagi machine learning di perangkat Android. NNIPI dirancang untuk menyediakan lapisan dasar fungsionalitas bagi framework machine learning dengan level lebih tinggi seperti TensorFlow Lite dan KV2 yang membuat dan melatih jaringan neural. IPI ini tersedia di semua perangkat yang menjalankan Android 8.1. Itu IPI level 27 atau yang lebih baru. Nah, next. Nah, ini kita lihat untuk yang GPU-nya ya. Penjelasannya di sini di video ini cukup jelas tentang itu. Cuma 3 menit videonya. Kita mulai. Sebentar aku share sound. Belum aku kelupaan, aku share sound. Oke, ini kalian prefer pakai caption atau enggak nih? Oke, pakai caption aja ya kalau gitu. Oke, kita mulai.
Running inference on compute-heavy machine-learned models, such as face and contour detection on mobile devices, can be very demanding due to the device's limited processing power, as well as considerations such as battery life. While converting to a fixed-point model is one way to achieve acceleration, we've also had lots of feedback about GPU support. So now we're excited to announce a developer preview of a GPU backend for TensorFlow Lite. This backend leverages OpenGL ES 3.1 compute shaders on Android and Metal compute shaders on iOS. This release is a pre-compiled binary preview of the new GPU backend, allowing you an early chance to play with it. We're working on a full open source release later in 2019 and would love to hear your feedback as we shape it. Let's take a look at its performance. We've experimented with a GPU backend on a number of models, including 4 public ones and 2 internal models that we use in Google products. The results showed that the GPU backend worked 2 to 7 times faster than a floating point CPU implementation. You can see the GPU inference time in orange and the CPU inference time in gray. We tested this on an iPhone 7, a Pixel 2, and a Pixel 3 amongst others. And this was the average inference time across 100 tests on each of these devices for each of these models. The speed up was most significant on more complex models, the kind that lead themselves better to GPU utilization. On smaller and simpler models, you may not see such a benefit because of, for example, the time cost of transferring data into GPU memory. So, I'm sure your next question is, how do I get started? Well, the easiest way is to try our demo apps that use the GPU delegate. We have written a tutorial to walk you through this, and I'll put a link to it in the description for this video. There's also a couple of really nice screencasts showing you how to get up and running quickly. There's one for Android and one for iOS, and I've linked to them too. For Android, we've prepared a complete Android archive that includes TensorFlow Lite with the GPU backend. When you use this, you can then initialize the TensorFlow Lite interpreter using the GPU backend with this code. On iOS, in C++, you can use modify graph with delegate after creating your model with this code. All of this is done for you in the sample app, so download it and give it a try. Now, not all operations are supported by the GPU backend at this moment. Your model will run fastest when it uses only the GPU-supported ops. Others will automatically fall back to the CPU. To learn more about GPU, including a deep dive into how it works, check out the documentation on TensorFlow.org, which also has a bunch of details on optimizations, performance best practices, and a whole lot more. This is just the beginning of our GPU support efforts. We're continuing to add more optimizations, performance improvements, and API updates all the time, but would love to hear your feedback on our GitHub page. We'd also love to hear your feedback on YouTube, so don't forget to hit that subscribe button, and if you have any questions or comments, just please leave them in the comments below. Thank you.
Oke, itu tadi dijelasin ya tentang TensorFlow Lite Experimental GPU Delegate. Nah, ini kalau Metal tadi yang buat iOS ya. Ini yang buat Android shader. Oke. Nah, delegate itu atau delegasi itu memungkinkan akselerasi perangkat keras model TensorFlow Lite dengan memanfaatkan akselerator di perangkat seperti GPU dan Digital Signal Processor atau DSP. Nah, ini delegate. Jadi ada interpreter, ada CPU, operation kernel, accelerator delegate. Nah, dia itu kayak nge-select yang paling bagus gitu. Jadi misal ada 3 gini, jadi dia akan nge-select yang paling bagus. Nah, ini inputnya. Terus dia ambil yang paling bagus gitu, kayak setelah punya model, terus kita cari yang paling bagus gitu. Nah, ini ada activation di sini. Kayak gitu, terus dia akan ini option, jadi dia akan milih dari optionnya gitu. Ini option. Oke, kayak gitu untuk yang delegate. Nah, ini ada teknik. Di sini ada teknik quantization. Itu untuk mengurangi presisi weight dan bias. Terus ada weight pruning. Itu mengurangi jumlah parameter, terus ada model topology transform. Itu untuk mengubah bentuk model. Itu ada tensor decomposition sama distillation. Nah, kenapa pakai yang quantize gitu ya? Kenapa quantize? Nah, semua jenis CPU platform disupport. Jadi kalau semua quantize itu dia bisa support ke semua jenis CPU platform. Terus dia mengurangi latensi dan interference cost. Terus juga low memory footprint. Terus dia low execution on hardware restricted to or optimized for fixed point operation. Terus optimize model for special purpose hardware accelerator atau TPUS. Terus ini ada step dalam optimizing, itu jumpstart. Yang pertama, use pre-train or retrain model. Terus kita custom model, itu develop and deploy custom model. Nah, di sini terus performance atau optimize itu performance, explore option, validate, and accelerate model. Habis itu optimize itu model optimization toolkit. Oke, ini yang tadi performance sudah kita bahas, terus yang optimize tadi juga udah ya. Nah, sebelum masuk ke part 2, kira-kira ada yang mau bertanya nggak nih tentang yang part 1 tadi? Oke, masih belum ada nih yang mau bertanya tentang part yang pertama tadi. Oke, kalau belum kita lanjut part yang kedua. Oke, kita lanjut ya, masih belum ada. Kita lanjut part yang kedua, yaitu taking a look at the saved model format. Nah, ini saving, converting, optimizing a model. Itu TensorFlow, dia save model, terus pakai TensorFlow Lite converter, baru kita bikin TensorFlow Lite model. Jadi secara ini kayak pembuatannya dari saving, converting, dan optimizing model gitu. Oke, kita next. Nah, ini TensorFlow Lite converter. Di sini ada TensorFlow API, itu ada Keras atau low level API. Yang merah ini infrastruktur, yang hijau itu file format, yang putih abu-abuan ini yang data type, terus yang biru itu backend-nya. Jadi TensorFlow Keras itu ada TensorFlow.keras untuk modelnya. Dia baru di save model juga. Terus low level API itu ada concrete function, baru juga ada save model. Nah, setelah di save modelnya itu baru dibuat TensorFlow Lite converter. Jadi baru dijalanin yang TensorFlow Lite TF Lite converter. Nah, baru ada yang namanya TF Lite flat buffer. Ini terus setelah itu kita ke TF Lite interpreter. Nah, baru ke backend-nya ada NNAPI, ada GPU, ada CPU. Jadi yang mulai TensorFlow Lite interpreter ini udah ke mobile device. Kalau yang sebelumnya tadi itu yang developer workstation. Jadi itu secara singkat sih ini ada flat buffer itu untuk in-place access of serialized data without first parsing atau unpacking ini ya, tanpa dia unpacking gitu. Oke, seperti itu untuk TensorFlow Lite converter. Nah, untuk selanjutnya ini parameter for conversion. Itu ada input model, save model itu preferred, itu TensorFlow.lite.tf Lite converter from save model. Terus Keras, model instant HDF5 file, tf.lite, tf-lite converter, from Keras, from _Keras_ model. Terus concrete itu concrete function tf.lite, tf-lite converter from concrete _function. Jadi yang di tengah ini Python API yang di preferred gitu ya. Terus outputnya baru TF-Lite model. Seperti ini parameter conversionnya. Nah, tadi ada save model ya, kalau kita lihat. Nah, save model itu standar untuk serialize sebuah TensorFlow model. Akan ada metagraph, sebuah data flow graph, untuk menyimpan metadata yang membantu prediksi model. Ada snapshot dari train model, jadi dengan weight dan computation model. Tidak memerlukan bundling code model required. Support model versioning. Oke, kita demo contoh yang pertama ya. Kebanyakan selalu dimulai dari yang linear regression gitu ya. Oke. Sini setup, try, TensorFlow version 2.x. Save pass. Import patlib, numpy, smp, matplotlib, pyplot splt, sama import TensorFlow stf. Sini kita lihat versionnya. Nah, di sini karena tadi kita 2.x, jadi yang kita pakai 2.8 ini ya. Kalau selain itu kita pas, jadi selain yang 2 titik gitu kita pas. Terus di sini kita create a basic model from Y sama dengan MX plus C. X-nya ini min 1, 0, 1, 2, 3, 4. Y-nya min 3, min 1, 1, 3, 5, 7. Ini simple keras model. Terus kita panggil yang tadi TF, TensorFlow. Keras model sequential. Dan unit 1, input shape 1, model compile, optimizer, SGD, stochastic, gradient descent, loss mean square error. Model.fit, X, Y, epoch-nya 200. Step per epoch-nya 1. Ya, kita generate save model, export directory, save model 1. Convert save model to TF Lite. Kita bikin converter tf.lite, TF Lite converter from save model export directory. Tadi kita save model di export directory. Terus ini TF Lite model converter.convert. Kita convert save modelnya ke TF Lite. Terus TF Lite model sama dengan matlib.pet model.tf Lite. Oke, breakpoints-nya 888. Kita initialize the TF Lite interpreter to try it out. Load the TF Lite model and allocate tensor. Jadi di sini kita allocate tensornya, interpreter, model, content sama dengan TF Lite model yang udah tadi kita buat. TF Lite model yang ini. Interpreter.allocate tensor. Terus input detail, get input and output tensor. Interpreter, get input detail sama get output details. Terus test the TF Lite model on random input data. Terus input shape, input detailnya 0. Shape, input, output, ini list kosong. In for loop, in range 100, input data sama dengan np.array, np random sample input shape, the type np float 32. Interpreter set tensor, input details 0 index, input data, interpreter invoke, TF Lite results, interpreter get tensor output details 0 index ini buat dapat get tensor yang outputnya gitu ya. Jadi yang output details ini output details. Terus test the TensorFlow model on random input data. Nah, TF result model, TF constant input data, output data. Ini yang input data, output data sama dengan np array, TF result, input append, input data 00, index 00, output Paint index 00. Terus kita visualize modelnya, matplotlib inline. Oke, input, output, R untuk warna garisnya red, plt show. Oke, ini grafiknya tadi untuk yang visualize model yang tadi kita buat. Terus kita download TF Lite model file. If you are running this notebook in a collab, you can run the send below to download the TF Lite model to your local disk. Di sini untuk kita download gitu ya. If the file does not download when you are running the cell, try running the cell a second time. Kita coba ya. Ini ke download ya. Ya tadi ke download sih. Oke, ini untuk yang contoh yang linear regression gitu ya. Terus ini buat download TF Lite modelnya. Nah, untuk yang transfer learning, demo example 2 yang transfer learning, bentar masih loading. Oke, transfer learning with TensorFlow for TF Lite. Setup sama kayak yang tadi. 10 menit. Import NumPy, Matplotlib, TensorFlow. Nah, ini ada TensorFlow Hub buat yang tadi ya. Transfer learning with TensorFlow Hub for TF Lite. TensorFlow Dataset atau TFDS. TGDM. Ini pakai TensorFlow version 2.8, TensorFlow Hub version 0.12.0. GPU-nya found, GPU device found ditemukan ya. Terus kita select the hub or TF2 model to use. Hub modules for TF1.x won't work here. Please use one of the selection provided. Okay. Di sini kita using TF Hub Dev Google TF2 Preview MobileNet V2 Feature Vector /4 ini ya. Terus data pre-processing, use TensorFlow dataset to load cat and dogs dataset. This TFDS package is the easiest way to load retain data. If you have your own data and are interested in importing using it with TensorFlow, see loading image data. Oke, ini kita pakai TensorFlow dataset. Ini besok kita juga akan belajar ya tentang TensorFlow dataset di hari Jumat. Ini kita pakai TensorFlow dataset. So, kita bahas di data pipeline juga tentang itu. Terus di sini the tfds.load method downloads and cache the data and return a tf.data.dataset object. This object provides powerful, efficient method for manipulating data and piping it into your model. Since cat and dog doesn't define standard split, use the subsplit feature to divide it into train, validation, test with 80%, 10%, 10% of data respectively. Jadi 80% training, 10% validation, 10% test. Oke, kita pakai yang tadi split all, subsplit. Nah. Oke, bentar. Coba. Bentar ya, aku coba buka di yang VS Code. Has no attribute all. Oh, satu-satu ini. Train subsplit. Oke, bentar. The float atau langsung yang ini. Berarti ini kita ubah. Semuanya cuman adanya yang train sama test. Harusnya pakai yang ini sih, yang full all. Special name, split, union, equivalent. titik-titik ini. Oke, kayaknya splitnya langsung deh, jangan di situ. Oke, train tadi 80. Present. Tes 10. Validation. Kita lihat kalau label validation namanya apa ya di sini. Oke, ada validation. Validation. Kita coba. Oke, error. Failed to capture URL. Get docs. With info as a supervised splits. Karena splitnya nggak mau. Filter info split. Ini harusnya buat nge-split all, tapi kayaknya karena aku sama yang lain running ini itu udah di bulan-bulan lalu gitu, jadi kita udah pakai code yang emang udah kita jalanin gitu. Nah, kayaknya si split all ini udah nggak ada gitu, si all ini. Jadi tadi kan errornya karena objek split tuh nggak punya atribut all gitu. Nah, kalau pakai Google Colab tuh kadang suka gini karena kadang tuh banyak yang udah ke-update gitu loh. Split all. Kalau aku lihat tadi di sini itu harus dibuat si ini ya kayak di splitnya di sini karena tadi kalau aku giniin contohnya itu si split ini langsung split gitu. Split. Tapi karena aku coba ikutin yang ini, yang kayak gini langsung di split di sini, itu masih ada error. Tapi ini kayaknya oke, ini split karena kan awalnya disimpan di satu split aja gitu ya. Terus biar splitnya langsung manggil yang train atau yang ini gitu ya. Nah kalau yang di sini, kalau mau dibikin kayak gini, splitnya langsung gini, itu harus manggil kayak train sendiri, tes sendiri, baru nanti yang split ini dipakai di train satu, di tes satu gitu. Nggak apa-apa sih kalau gitu, coba ya, kita coba kayak gitu. Train dataset, tes dataset, sama si file dataset. Oke, ini masih error karena to get the URL. Oke, ini karena the resource you are looking for may have been removed, edit name changed, or temporarily unavailable. Oke, ini yang error emang dari datasetnya juga karena udah nggak tahu nih kayaknya keubah ya. Code-nya tadi ke remove atau apa gitu ya. Kita coba lihat langsung di TF datasetnya. Research model dataset. Kita lihat sih. Cat and dog. Oke, yang TensorFlow Hub. Oke, kita nggak yang teks, tapi yang image. Kita yang image, terus cat and dog itu tadi ini. Oke, nggak ada. Iya, emang udah nggak ada nih kok tensor yang cat and dog datasetnya. Dataset cat and dog ya. Cats versus dog. Oke, udah nggak ada kayaknya. Soalnya tadi URL-nya yang aku masukin kayak gini ya. Nih. File or directory not found. Oke, kita lanjut aja ya. Aku jelasin aja ya buat code-nya. Jadi kalau tadi kita mau nge-split nih. Mau nge-split dengan bobotnya itu 80% train, 10% validation, 10% test. Nah, terus di sini kita split train sama kita lihat feature labelnya. Terus kita format datanya, kita bikin fungsi format image. Image label ini untuk nge-resize. Jadi nanti image size-nya tuh image, image size dibagi 2550. Terus batch size-nya itu 32. Train batch-nya, train example, shuffle 6 example, bagi 4. Terus map, fit, format image. Ini ya, batch size-nya 32. Ini bisa kita naik turunin. Oke, terus validation page sama private 1, test page, batch-nya 1, example. Oke, itu sebentar aku coba cariin, kayaknya aku ada yang udah ada hasilnya. Siapa tahu bisa ditampilin karena ini nggak bisa di running ya. Terus ini defining the model with text to put a linear classifier on top of the feature extractor layer with the hub module. For speed, we start out with a non-trainable feature extraction layer. Oke, sebentar. Oke, ketemu. Tadi kita sempat error di ini ya, yang tadi subsplit, split, split ini ya. Oke, terus tadi kita define tunning, false param, type boolean, filter extractor, hoop.keras, ini layer, module handle, input shape image size plus 3, fv size, dan do define tunning. Ini kalau kemarin yang dibilang itu ya, yang kalau kita pakai transfer learning itu ada yang namanya fine tuning ini ya, fine tuning. Oke, terus print building model with kita model sequential dense num class activation softmax. Sini kita training model if do tunning, model compile. Ini kalau berarti kalau dia nggak do tunning, dia akan ngelakuin yang else-nya gitu. Epoch-nya 5, terus history, model.fit, train batch, epoch sama dengan epoch, validation data, validation page. Ini cat versus dog, save. Save model, catch versus dog. Oke, ini terus convert ke TF Lite sama kayak yang tadi. Nah, di sini ada yang namanya quantization tadi. Post training quantization, the symbols from a post training quantization, quantize weight from floating point to 8 bits of precision. This technique is enabled as an option in the TensorFlow Lite converter. Inference weights are converted from 8 bits of precision to floating point and compute using floating point kernels. This conversion is done once and cache to reduce latency. To further improve latency, hybrid operators dynamically quantize activation to 8 bits and perform computation with 8-bit weight and activation. This optimization provides latency close to fully fixed point inference. However, the output are still stored using floating point, so that the speed up with hybrid ops is less than a full fixed point computation. Terus ini converter. Tadi kita pakai yang quantization itu yang optimization, TF Lite, optimize, default. Terus ini post training integer quantization. We can get future latency improvement, reduction in peak memory usage, and access the integer-only hardware accelerator by making sure all model math is quantized. To do this, we need to measure the dynamic range of activation and input with a representative dataset. You can simply create an input data generator and provide it to our converter. Jadi kita bikin dulu fungsinya representative data generator, terus kita bikin looping, for loop, input value, in test batch, text 100, yield, input value. Ini yang tadi yang to do this nih ya, we need to measure dynamic. Nah, ini buat dynamic range. Terus di sini converter dari representative dataset sama dengan representative data chain. The resulting model will be fully quantized but still float input and output for convenience. That do not have quantized implementation will automatically be left in floating point. This allows conversion to occur smoothly but may restrict deployment to accelerator the support float. Now I have fully integer quantization to require the converter to only output integer. Jadi yang integer. One can specify Oke, ini yang cat and cock ya. Homepage image classification tuh kita sesuaiin ya. Get versus dog. Press. Gimana kalau kita langsung load ini, split info through as supervised. Data to data set. Oke, itu udah. Terus Treated string or bytes like object. Berarti ini kalau emang harus string, berarti ini split. Oke, ini nanti aku coba deh satu-satu daripada kita nunggu yang ini ya. Karena ini yang all-nya itu nggak bisa dipakai. Oke, itu nanti aku coba sebelum aku kirim jawaban yang belum aku kirim code-nya, nanti aku benerin dulu. Oke, itu tadi kita lanjut dari yang full integer tadi. Terus ada yang finally convert the model. Nah, kita convert modelnya. Terus test the TF Lite model using the Python interpreter. Terus ini load TF Lite model and allocate tensor. Ini interpreter TF Lite, interpreter model underscore pad sama dengan TF Lite model. Padnya ya, tadi model pad. Oke, terus ini input outputnya sama kayak yang waktu tadi kita lihat di yang linear regression. Terus di sini get the result for the randomly sample test image, sama ya kayak yang tadi juga kita get the result dari yang random input. Terus ini test label sama test image, list kosong, image, label in, tag UTM, test batch, text 10. Terus yang lanjut, ini title, utility function for plotting, utilized for plotting. Class name-nya cat sama dog. Di sini ada dua kelas gitu ya, cat sama dog. Terus def float image, prediction array, true label image, prediction array, true label, image-nya prediction array index E, true label index E, image index E, penalty create false. Terus xt, gt gitu, terus image, and paste, quiz, image itu harusnya bisa kalau di sini tuh. Ini ya utility nanti bisa kayak indeksnya digeser-geser gitu loh kalau udah di visualize input. Terus ini create a file, terus have label yang tadi cat sama dog. Ini kita download tadi ya modelnya, convert, download model, convert model. Oke, terus ini yang buat di mobile apps-nya. Only in case you need to try out more sample. Nah, ini make a dir, p, test image, p, from pill image. Ini ya kalau kita, in case kita butuh more sample gitu. Oke. Kita lanjut. Nah, tadi ada post-training quantization, itu mengurangi precision dengan 3 kali lipat lower latency. Sedikit degradation pada akurasi model. Optimization mode itu default both size and latency atau size dan latency. Thus efficiently represent an arbitrary magnitude of range. Quantization target specification. Ini post-training integer quantization tadi udah ada juga kayak TensorFlow, estimator or keras, Self model plus calibration data, TensorFlow Lite converter, TensorFlow Lite model. Post training. Ini yang post training itu yang udah ada tadi ya, post training. Nih, yang tadi ya post training integer, post training quantization. Nah, di sini path in optimization, nah, optimize your model in a nutshell. Jadi di sini post training quantization, terus kita optimize for ini kita isa size-nya aja, latensinya aja atau dua-duanya. Terus kita have a representative dataset kalau kita punya. Nanti kita langsung post training integer quantization, terus use fallback ops atau limit to integer 8 ops, terus baru dapat model quantize ops kalau yang integer 8. Kalau yang fallback itu model quantize and float ops. Kalau kita nggak punya representative dataset, berarti kita langsung model quantize weight only. Nah, kayak gitu.
Occasions we need to deploy a machine learning model on cell phone, on microcontroller, or a wearable device like a Fitbit. Usually machine learning models are of bigger size, so if they're running in a cloud on a big machine is okay, but if you want to deploy them on edge devices, by edge devices I mean all these devices which I just mentioned, then we need to optimize the model and reduce the model size. So when you reduce the model size, it fits the requirement of a microcontroller. Microcontroller might have only few megabyte of memory, so it meets the requirement of limited resources, and also the inference is much faster. In this video we will look into a technique called quantization, which is used to make basically a big model a smaller one so that you can deploy on edge devices. We'll go through some theory and then we'll do coding as well as usual. We'll convert a TensorFlow model into TF Lite model and we'll apply quantization. Let's begin. Devices like microcontroller or wearable devices have less memory compared to your regular computer, and quantization is a process of converting a big TF model into a smaller one so that you can deploy on edge devices. By edge devices I mean all these devices. Small devices are called edge devices. And if you look at your neural network model, when you save this model on a disk, you are essentially saving all the weights. These weights are float. Sometimes they use float 64 precision, which is 8 byte. So to store one number, you are using 8 bytes. Sometimes you might be using 4 bytes. So let's say you're using 4 bytes to store your one weight. And by the way, I've shown you a very simple neural network. Actual neural networks are much bigger, so many layers, so many neurons. Now, if you convert this weight into integer, let's say you are just approximating this number from 3.72 to 3, then you can reduce your memory storage from 4 byte to 1 byte. This is int 8, by the way. And if you're using 8 bytes, and if you go from 8 bytes to 1 byte, that is a huge saving in terms of memory. So quantization is basically converting all these numbers which requires more bytes to store in each individual number into, let's say, int. So it's not always int. Sometimes you are converting from float 64, which is 8 byte, to float 16, which is 2 bytes. Even that case also you are reducing the memory size. So that is basically quantization. It's a simple approach. Now you're not blindly converting these weights into numbers. For example, here you have 3.23. You might not be saving that as 3. Maybe you are saving it as 4. There is an algorithm that you have to apply, and I'm not going to cover that. You can read the research paper online on how exactly quantization work. In this video, I will just keep it to, a very higher level. Higher level, you are basically reducing your precision and each individual weight that you want to store. You are using maybe int 8 or float 16 so that overall size of the model can be reduced. And obvious benefits are you can deploy your model on a microcontroller which might have only few megabyte of memory, and even the prediction time is much faster. So the performance when you're actually making prediction is much faster if your model is, let's say, int 8. There are two ways to perform quantization in TensorFlow: post-training quantization and quantization await training. In post-training quantization, you take your trained TF model and you use TF Lite convert. By the way, if you don't know TF Lite is used to convert these models into smaller ones so that you can deploy on edge devices. Now, when you do this conversion, you can see this is a bigger circle, this is little smaller circle, so it will already reduce the size because the memory format that it is using is different. But if you apply quantization at the time of conversion, it will make it even more smaller. You see the smaller circle here on the right hand side? Previously it was bigger, but when you apply quantization, the model size is much smaller. Now this is a quick approach, but the accuracy might get suffered. So the better approach is quantization aware training. In this case, you take TF model, then you apply quantize model function on it, and you get a Q model in TensorFlow. We are talking about TensorFlow. And then you do training again. So this is more like a transfer learning. You are doing fine tuning here. So you're taking your model, quantization, you're doing quantization, and on quantized model, you're fine tuning that. You are running the training again, maybe for fewer epochs, and you get fine tuned quantized model, and that you convert again using TF Lite. See, if you want to deploy TensorFlow model on edge devices, you have to use TF Lite. You have to do TF Lite conversion. That step cannot be avoided. This approach is little more work, but it gives you a more accuracy. Now let's do some coding so that you get an exact idea.
Still confused where you upgrade skills to be a data scientist or analyst? At Pacman Academy, you can learn practical data skills in 6 to 14 months with live interactive class, self-paced learning video, and real-world project labs. We help you to land your dream.
I'm going to use a notebook which I created in one of my deep learning videos. So if you go to YouTube, search for Core Basics Deep Learning, you'll find my tutorial playlist. Here I made a video on digits classification. So I have taken a notebook from here. If you don't know the fundamentals, I highly recommend you watch this video first and then you continue with this particular video. So here, as you can see, I have trained a handwritten digit classification model in TensorFlow, and then I have exported that into a saved model. See, model.save model, and that created this save model directory, and the size of this directory is around 1 megabyte. I have a very simple model, but in reality, if you're using a big complex model, the size might go even in gigabytes. Now, first approach we're going to explore is post-training quantization. For that, you will use TF.Lite module. So TensorFlow has this TF-Lite module, which allows you to convert your model into TF-Lite format. You will use TF-Lite converter format, and a method that you're going to use is from saved model. So here you can supply the directory where you have your saved model, and this will return you a converter, and you can simply call converter.convert, and that will return you a TF-Lite model. So this approach is what we discussed during our presentation, which is without quantization. So even if you directly convert using TF-Lite model, your model size will be little less, but if you use quantization, it will be even more less. So this is without quantization, and if you look at the size, by the way, this is just the bytes, okay, and you can get a rough understanding. It is around 312 kilobyte. Now I will use quantization. For quantization, just copy paste this code and only add one line, and that line is optimizations. Optimizations is equal to this, and now you got your quantized model, and the size of this quantized model is much less. It is almost 1/4. So by doing this, you converted this into an integer. You converted all the weights to integer. Okay. And if you want to read more about this API and what other options you have here, I'm going to link an article in a video description below where we have used this method, which is just quantizing the weights. You can also quantize activations too. That will be even more better. That's called full integer quantization, and you have to use this particular code. Okay, now let me save these two models into a file. So I'm going to just write this model into a file. So I will call it, I'll first save non-quantized model, and the extension is TF Lite. Since it's a bytes data, I will use write and bytes mode as f, and then f.write, well, this particular one. And I can copy paste this and do the same thing for quantized model. So here, when I execute it, both the files are returned here. See, this model is how much? 312 kilobyte without quantization. With quantization, 82 kilobyte. Hooray! 1/4 size reduction. Now
Anvil is a platform for building full-stack web apps with nothing but Python. Anvil lets you build your app's front end by either dragging and dropping components in the Visual Designer or by adding components using Python code. No HTML, CSS, or JavaScript required. Let's look at how you can use the Anvil editor to create a user interface.
Now let's talk about quantization aware training. Post-training quantization is quick, but the accuracy might get suffered. With quantization aware training, you can get better accuracy. You need to first import the model optimization called TF mode from your TensorFlow, and I will use a method called quantize model. Okay, so I'm going to use this method called quantize model here, and let me just save it in a variable so that I don't have to write this whole thing all the time. And I'm going to, this is basically a function which I'm going to call on my regular model. My regular TensorFlow model is this. You see model variable? I'm applying that quantize model method on that, and I get my quantization aware model. So if you go to my presentation, say this is the first step. On your regular TF model, apply quantize model function, you get quantize model. Then you have to fine tune. This is like transfer learning. You have to run training on that model again, maybe with less epoch. So I'm going to compile this particular model. Okay, and for compile I have used same parameter as I used here originally, and I'll quickly display the summary. Before fine-tuning, you need to compile, and then the summary just shows how many parameters, non-trainable, trainable, and so on. And I will use the training only for one epoch. Okay, I think one epoch is good. You're already getting 98% accuracy, and let's measure that on my test dataset. Test dataset accuracy is also like 97%, so my accuracy looks beautiful. And now I'm going to use again the same converter. Okay, but for this converter, previously we used what? From save model, because we were loading from the disk. Here I will use a different API, from Keras model. So you use from Keras model if you are loading an in-memory model. Okay, and then that will get you converter, and then you are using the same technique. See, converter optimizations. Let me do this. So optimizations. So here you are applying quantization here, and then you are actually running quantization aware training. So it is two-step. You first run quantization aware training, and then during the TF Lite conversion you apply the quantization. Okay, and I will save it in a different variable. Okay, and let's write this as well to a file, because these are just the bytes that you got. You need to write it to a file with extension TF Lite. So now what I got, so if you go back to my diagram, you quantize, then you do fit for fine tuning, then you do your ultimate TF Lite conversion. Okay, and the size of this model is 80 kilobyte. Without quantization aware training, it was 82 kilobytes. So now we are reducing it even further. And the main benefit of this model is the accuracy is little better compared to the other approach that we took. So just to quickly summarize, in this notebook, we trained our model in a usual way. We saved it to our hard disk. We saw the size was 1 megabyte. Then we did post-training quantization. Our quantized TF Lite model was around 300, and without quantization it was 312 kilobyte. Then we got 82 kilobyte, 84 kilobyte model, 82 kilobyte actually. And then when we ran quantization aware training, we got 80 kilobyte model. But the main benefit of this model was the training accuracy is much better. I'm going to link few articles in the video description below, so you can read through those articles. The purpose of this video was just to give you overview of quantization. This notebook is available in video description below. So friends, please try it out. Just by watching video, you're not going to learn much unless you practice on your own. If you like this video, please give it a thumbs up. That is the session fees, that is this training session fees. You can do at least that much. If you don't like it, give it a thumbs down. I'm fine, but leave me a comment so that I can improve in the future, and share it with your friends. I have a complete deep learning tutorial series, by the way. You see, complete deep learning tutorial series which you can benefit from. There are so many exercises as well.
Oke, ini tadi untuk ngejelasin tentang quantization ya. Nah, tadi kan ada di code-nya itu yang post-training quantization itu ya. Tadi dibahas semua yang quantization di situ. Nah, tadi ada yang quantization, terus di bawah ini ada yang optimization toolkit, quantization and pruning. Tadi juga ada ya waktu di slide berapa ya tadi? Itu butuh pruning. Di belakang sempat ada butuh pruning sama butuh yang optimization toolkit gitu ya. Kita coba dengerin yang ini ya untuk lanjutannya tentang yang model optimization toolkit.
Okay, we'll get started. So, hi everyone, I'm Suhash, and I'm going to talk about the TensorFlow Model Optimization Toolkit, which we have techniques for quantization and pruning, and feel free to ask questions or interrupt along the way. I want this to be like super interactive. So what we're going to talk about today is the high level of what quantization is, the challenge it poses, and why it matters, and then more of the specifics on, in TensorFlow, what we are doing to work on quantization and pruning. So overall, quantization, the idea is that you have your floating point network, which your inference graph, which is a floating point program, and we're going to make modifications to this program in the general sense that we take these floating point calculations and make them lower precision. And the goal is to get as close in accuracy as possible while providing some performance improvements. So usually this involves, like, this is very general. There's some function from the floating point to the integer value. There's a process to do the conversion to make it valid for particular hardware. And then there's various algorithms we have to get these parameters needed for this function in the most efficient way. So this is really general, and what may not make sense now, but we'll make it more specific later.
Do the same conversion functions work for mobile devices as well as specialized hardware?
No, and that's one of the challenges, and we'll get through all the challenges. That's a really good question, and that maybe actually, so.
I had another question. Like, would you also be like motivating soon? Like, why is this not as simple as like a downcast from float to int versus
yes, it'll
broader
all make sense.
quantization?
Yeah, it'll all make sense.
Okay.
I hope. Okay.
We're obviously very interested.
So why does this matter? So the first thing is that the ML programs have lots of parameters, and we can, by using lower precision, we can instantly get these models a lot smaller, which can help with memory bandwidth and network costs of downloading models. Second, if you have all your calculations in integers, you can have lots of optimizations that make the execution super fast. Third, integers are super power efficient. So on mobile, this is really important. And then finally, this lets us explore a whole new avenue of hardware design where we can make custom chips, like C-Star was the first, then Edge TPU, the new TPUs, how are you having integer operations, and this can get us cheap, power efficient, fast hardware. Blah. Okay, so
I think it helps if instead of saying integer operations, you say fixed point, fraction operations.
So
that's what
so I avoid it because it's like only kind of fixed point. It's not like it is fixed point, but I've said fixed point in the past, and then folks always say it's not truly fixed point because fixed point applies like a rescale every time you combine the two values. And sometimes I get pushback, but so I'm gonna like avoid, because I used to say quantization, and then people say there's 100 steps of quantization. So the integers are the key here because that's what's providing the acceleration that's specific to what we're doing in the TensorFlow stack, and the specifics, I guess, will make sense after we go into the equations. So why is quantization hard? And this was your point of that we have different chips. So each chip has its own specific trade-offs it chose to make. Some may only support int8, some may support int16, some may want power of 2 rescales. Like all these really one-off decisions make the deployment story of how do you take a general TensorFlow program and put it on one of these chips really hard. Like for float, we're starting to get to a world where we can just say float can run anywhere. But for these things, there's not a lot of standardization on how to do this. The second reason it's hard is it often requires custom tooling because you need extra metadata that often can only be gathered by running inferences to know how to quantize the values. And we'll get more into that in detail. So there's often an extra step in the process. And then finally, for every specific ML problem, we don't have a good answer for how quantization will affect it. You can use the same architecture, but just do something else for your particular task with the outputs of that architecture. And quantization may help or hurt. And it's pretty empirical right now where we just try it and see, and we're still in the process of gathering a lot of examples. But one of the goals we need to work on in like ML research is understand these models more to determine how quantization error will impact things. So now more into the details. So currently what most hardwares implement and what the TensorFlow and TensorFlow Lite stack implement is affine quantization, this is like us milking y equals mx plus b since like 7th grade for the rest of our lives. So basically you uniformly distribute your range into fewer chunks than you had before. and then bucketize them. And this is effectively what all quantization is. Currently, we have different ways of gathering statistics to determine how to quantize. So going back to this picture for a second, we need some sort of min and max value to know how to quantize. So this implies that we need tooling to get this information. And we have two types of tooling right now. There's during training tooling, where you can incorporate this as part of your training pipeline. And at the end of the day, you have a trained model that has information on how to quantize it. And you can also do this post-training. And we'll talk about the trade-offs later.
I have a question. So why are your min and max not beyond the boundary of your possible values? Like, why do you choose, or do you like purposefully choose to leave some values out?
So yeah, the min and max, it's kind of a open question on what is the optimal min max given a tensor. And if I understood the question right, so you could choose to put your min max much smaller than your actual value seen, and you'll get some clipping. And depending on the model and the problem, we wouldn't really know if it's useful or not, because sometimes models don't care about those extraneous values, and sometimes they're the most important thing in the whole model.
I mean, the tricky thing is that like when you set your min and max, and if you're using like int 8, you only have 255 values between the min and max.
Mm-hmm.
Every activation has to be cast to one of those 255 values. If your min is minus infinity, if your max is plus infinity, that's really useless.
Yeah.
But if your mean is like 0 and your max is like 0.01, you can represent computations with a lot of precision. So it's the trade-off.
Yeah. So and we do different types of these depending on the model, and we've seen weird things where and it's always this battle between how much does the network care about these extreme values and versus how much does it care about the average rounding error along the way. So it's always this rounding versus clipping. That's like all, we just play with this a lot.
You mentioned about min and max being primarily influenced from training, right? But you would ideally like to also do this at inference, like keep there's a constant feedback
so
loop.
It was
from
training or post-training.
Okay,
so post-training meant inference or
okay.
like model compilation time if there's a step.
And can I just clarify? So the point is that it wouldn't be considered quantization if you just reduced like float 32 to float 16, for example, float 8 or whatever. So you still have a separate exponent and you have just kind of fewer bits. That's not considered quantization?
So that's technically it is like, so the textbook term of quantization, it is quantization. But the quantization we're talking about here is this integer quantization where you have a shared min-max. And
where you really don't want to have that
where you're
that
reusing that scale.
around the exponent.
Yeah.
You only want that.
So
that's the only thing that's super useful for the hardware. That
exactly. So like in other like DSP literature, it's sometimes called block floating point, where you have the exponent shared across all values of like a tensor, rather than one exponent per element. So in a way, float is just like per element quantization. So so during training, the idea of during training quantization is that you want to somehow get this network to be robust to this error that quantization introduces. So you emulate the effect of quantization in the forward pass. So if you ever see these like TensorFlow fake quant operations or the contrib quantize rewriter tool, this is its goal. It's saying, given a graph, we'll rewrite the forward pass to emulate the error due to quantization. And then in the backward pass, we'll do some tricks to skip over those different non-differentiable parts that quantization introduces. And then the goal is that backprop will magically make the weights better for quantization. And this can often get the best accuracy given a particular scheme of quantization, but it's also really hard to train sometimes. And it's machine learning, as we all know, is like the art of making as few changes to your training to get it to converge. And the second you do more, oftentimes you won't even converge if you go to too low of precision. And you just have to play around a lot if you try the training route. Additionally, it's the error introduced during training is specific for a particular target. So if you want the result of your training to be portable and work across many different chips, you're kind of in trouble now if they have different characteristics.
So by emulating quantization, does that mean on a forward pass after every like op, you just apply the quantization?
Yeah, and it's a bit trickier than after every op because it's after every rescale that the hardware expects. So like a specific example is like in TensorFlow, you have conv, bias, add, relu. In most of these inference backends, those are fused into one fat con by said ReLU. And your rescales are only at the inputs of the con and the outputs of the ReLU. So you should emulate quantization there. So you kind of need knowledge of what the target's expectations are to decide where to put it. So it's not just before and after every op.
And do you just use the current running max and min?
Yeah, so right now we do moving average. For certain models, we played with absolute min and absolute max, and it's really, sometimes we use schedules to slowly manually constrain it, and this is where the art part, and it's not really well understood how to do that generally. So right now for all the mobile, like all the vision models, we do moving average, and it seems to work pretty well, but we don't know if that's optimal at all.
That's it.
It just turns out backprop is kind of magical.
And backprop, you don't apply this at all?
Backprop, we use this thing called straight-through estimator, which the main problem with this quantization is that it's like a step function, so it's not differentiable. So we pretend it's an identity, and we just pass the gradient right through, and this like gets it to train.
It works in practice.
Mm-hmm.
And just to clarify, there's never a case where quantization is used in training just to speed up the training. To speed up the training, it's only used in training because of the idea that it would speed up inference. Is that correct?
So there is some work. I don't know if it's ever used in practice, but there's been a few papers over the years that do quantization for speeding up training as well. But this particular one is always, everything in this talk is the goal is for inference. And so this is purely to emulate what's happening at inference. And oftentimes it'll be slower to train these models than to actually just do a float one.
And just to be sure, I thought more than actually speeding up inference, the goal with quantization aware training is to actually reduce errors, right?
Yeah, but to reduce the accuracy that you get, that you lose when you eventually go to inference. But the ultimate goal of this whole tooling is to enable inference performance for some particular hardware. Mm-hmm. So that being said, we've been trying to work really hard to avoid the need for this in most general cases. Like during training will always be the most accurate because you're letting the network make up for it, but we think we can get pretty far with post-training techniques. So after training, the trade-offs are that you can't rely on this magical huge hammer of backpropagation to fix all your accuracies, but you can do some things. And additionally, the main benefit is that the user doesn't have to retrain, which is a pain to retrain because oftentimes it won't converge. You have to mess with hyperparameters. Your portability is gone. So here there's like a compile step, or sometimes, like you were saying, even at runtime, there's a step to collect these statistics to do min-max. So the second technique we have, so we'll get back to quantization for the majority of the talk, but I just want to mention pruning. So the other technique we have is pruning, which the goal is to result in tensors in your model that have many zeros. And these, so if you do arbitrary pruning, where your resulting model has many zeros, it's much more compressible. And additionally, if you have a certain structure to your pruning or a certain percentage of sparsity, you can have optimized kernels that accelerate things. So yeah, so the benefit is that you have so many repeated values now that you can just like zip your file and you're good to go. And then if you actually have hardware support for sparsity, you can get faster kernels. And one more point on pruning, which I think is kind of cool, is that it's all the zeros are, since you have so many repeated zeros, and zeros in quantization we represent exactly, it actually works really, really well with quantization and often helps quantization, which is kind of, they're like compressing in two orthogonal ways, which is kind of neat. So now we'll talk about all the tools. So yeah, last year we released this model optimization toolkit, which is a suite of TensorFlow and TensorFlow Lite tools that aim to make all these techniques doable and let us play around with trying out new things with quantization and pruning. So you can check that out here. So here's my world famous hand. Like this one on Twitter, and this is my hand. I just remember. No. So
Jeff Dean tweeted your hand, I think.
Yeah, that's true. So yeah, we've been reusing these pictures way too much, though. Yeah, so we have quantization and sparsity. So first, we'll deep dive in all the tools in quantization and a bit more detail on how we actually do quantization. So The first thing we've done in TensorFlow Lite is try to understand for many of the canonical models all the operations that are in there and what are some standard recipes on how to implement these fixed point quantized kernels. And the goal here is that we want some sort of endorsement for a new hardware that comes in. And we know that this is going to be like a work in progress because new chips are coming all the time. They have different constraints and they don't want to listen to one standard. But we want to be like some reference point to where we can compare, oh, this new quantization scheme, how does it compare to this? So the goal with this is for a bunch of CPU reference ops that have been tried on many models and we understand them to some extent. So this is a bit more detail on how we actually do the quantization. So the bottom number line is the floating point scale, and that histogram is a pretend distribution of values in a particular tensor. And the idea of quantization is instead of wasting all our bits representing this range that we don't even use, let's figure out only the part that the histogram lies in and only represent that with a smaller number of bits. So the top number line is the integer equivalent of that, where we took that histogram and we just used these 255 buckets to use to represent the number. So this is just that same affine equation. We at inference time, we actually have we changed this min-max to two different things called scale and 0 point. And scale is the floating point size of every bucket. And 0 point is an integer value that corresponds exactly to floating point 0. And this turns out to be really important. C-star didn't do this, and it resulted in a lot of bias issues. For every multiply accumulate you have, if you don't represent 0 exactly, you just push this bias. And then it also has a convenient thing of oftentimes in models we do padding, and it's like just 0 is just a special number that we have to represent. But the main thing is the accumulate thing. Mm-hmm. So this is just to give some insight into what these tools are actually, why do we need the information? So we won't go too much into depth here, but here's the summary of our quantization spec. And we have per axis symmetric weights, per layer asymmetric activations, and then the 0 point is all these things are in a signed integer value. And I'll explain each of these actually, because right now they won't make any sense. So the first part of the specification is symmetry. And the idea here is, do you want to make your scale be able to represent values that are really not centered around 0? And this means often that 0 point, I'll go back to the equation real quick, that 0 point here, do we want to have the cost of that addition? And depending on where this happens in your math, it can be really expensive or not too expensive. And so for symmetry, we've decided to make weights symmetric. And the reason is that since weights are constants, the 0 point is multiplied by the dynamic activations, and the activations are dynamic. So this is a cost that you'd have to do that's dependent on the input every time. So having weights be asymmetric, every inference has a cost that's additional. And so weights being symmetric avoids this whole 0 point multiplication with activations. And yeah, maybe we can answer more later, but I won't go too much in depth here. So it's faster if we make weights symmetric. And activations, they're only multiplied by a constant value. So having them have this 0 point is not too expensive. So we leave them asymmetric, and the activations are often like ReLUs and stuff, which are super asymmetric. So we'd be throwing away a bit if we don't do that. Cool. So the second thing we can play around with in quantization is the granularity in which we decide to have these min-maxes or scales. And traditionally we were doing per layer quantization or per tensor quantization. For a given tensor, you only have one min-max, but it turns out for convolutions and depth-wise convolutions, often each channel of the convolution has a really different distribution. And when you only have one scale or one min-max for the entire tensor, you're doing a really poor job in each of these distributions. So the idea of per channel quantization is you have a min-max per channel. And since this is not in the inner loop of your kernels, it's really not too expensive and gets a huge benefit in accuracy, effectively like an extra bit. So now to the tools. So the tool fragmentation is all, how do we get these min-max values that we need to do the quantization? And so for weights, it's super easy. Weights are static, so we can anytime just look at the weights, read the min-max, and quantize using those min-max. So the problem always comes in dynamic values and activations that you can only get an idea of the distribution by actually running realistic inputs. So the first, like most naive, simplest idea on how to do quantization is, let's read the min-max at the second we know it, which is right at inference. So during runtime, our graph is actually different. Before our expensive multiplies, our matmos, we take the float input value, measure the min-max, use those to quantize on the fly. So this is like a ON operation of quantizing on the fly. Then get the speed up of doing an int8 and int8 multiply on your matmul, and then go back to float at the end. So the idea is here is you get the most realistic min-max range for your activations because you're using the one at this for this particular inference. The flaws are that you can only really do this on chips that have float support. The second time we could do this is if we want the whole graph to be integer, we want to avoid this runtime cost of measuring the min-max because we don't want any float on any edge of this graph. So what we can do is simply move that to compile time. And so you have your float model, and we want to do some post-training figuring out of what the min-max values are for all these dynamic values. So to do this, we need some representative data that we can run through the model, collect ranges then, and then fix those min-max values for the activations. And this means that we're not using the perfect min-max like we were for hybrid quantization before. But we are working on getting a representative one, and we never have to have float in our inference graph. So this can go to all those integer accelerators.
I had a question kind of related to the previous slide. So the choice of whether to do hybrid or not, is that multifaceted, like based on improving accuracy, because now you get better min-maxes, but also the hardware needs to support the float biases, right?
Yeah, so it's really problem specific. So we'll get a little bit into that later as well, but the short answer is yes, it's multifaceted in that it's a good choice if you're going to CPU. It's a bad choice if you have models that have large activations. Like image models don't get a huge benefit from hybrid because your cost of doing this on the fly quantization is pretty big.
Mm-hmm.
And then accuracy really improves for models with small activations because you're kind of getting a more representative range for that small tensor.
And also if you want truly low latency inference, maybe it's not a good choice.
Yeah.
Right. Okay.
Mm-hmm.
I was going to ask, how much overhead do you get from the hybrid approach? I mean, it sounds pretty expensive if you have to.
Yeah, it can be, and it really depends on the model. So I think we have some specific numbers, but it really shines in models that are kind of memory bound, because your main cost is this n-cubed thing. Your activations may not be too big, but you're getting this huge benefit of really driving that matmul. So then the third tool is integer-only quantization, or during training integer-only quantization. So this results in a same compatible graph as that post-training integer quantization in the previous slide, but the difference is we're doing that, introducing the quantization into the training that we talked about before. So we're working on Keras APIs to enable this. So the way this looks the way this will look is you build your model as before, and you just wrap it in this quantized wrapper. And there's parameters too. We won't go into too much detail. For hybrid quantization, the way it looks is you train your normal graph for TensorFlow, and then you enable a flag in the TF Lite converter. So right now we have hybrid and the post-training only enabled in TF Lite because we want to make it general, but right now we only have specifics on the hardware capabilities of TF Lite at the moment, and we need to know these to be able to do this. So the way this looks is your normal TF Lite converter invocation, and you just add this optimization's default flag. And under the hood, this is just doing this hybrid quant of
just quantizing all the weights and leaving activations in float. So performance. So first off, all these approaches get similar model size reduction in that you're simply taking 32 bits, going to 8 bits, so you're getting a 4x reduction in size. For latency, here we see we do get a speed up in these image models, but for a lot of them, we don't see too much of a speed up as we would expect in quantization. And it's because that on-the-fly cost is actually pretty high at the moment.
What hardware is this? Is this just like a CPU?
This is all CPU. Mm-hmm. Yeah, so like on accelerators, this will be the integer ones will like really shine, and on custom accelerators. So accuracy, we do see an accuracy drop in a lot of these models, and a lot of this we are working on ways to nudge weights at different times during compilation to fix these accuracy issues. And so all this is not like the gold standard in what quantization can get in these techniques. It's just a starting point. So yeah, 4x reduction, you see a 10 to 50% increase in CPU and convolution models on CPU. And then for memory-bound models, you really see a lot more. And you often get most of the bang of the buck of quantization from hybrid in those models versus needing the full integer. That being said, for accelerators, you still need to go the full integer route. So post-training integer quantization. So this is also enabled in TF Lite. You train the TensorFlow the normal way you would a float graph, and then you provide one more option into the converter. And the way that looks is you do the same flag as before, optimization to default, but now we need some data to figure out those dynamic ranges at compile time rather than at runtime. So this data generator you provide needs to yield examples that you would expect to see in practice. And so for like image models, we just grab a few images from ImageNet, and usually we see like a couple hundred works well enough, but it's probably very problem specific. So under the hood, this is doing that post-training quantization where we measure the absolute min and absolute max we see for particular activations.
Why would a hybrid model be ever used? I mean, like ultimately you still have inferences coming in. So even if maybe the first one's like the first 1,000 slow, right? But like, after 1,000, you definitely have those statistics. Why would you ever not just then at that point compile?
That's a good question,
and just compile the graph with int?
You could do that. And so oftentimes it turns out for like the RNN models, you actually get an accuracy benefit from hybrid. Even
if you had a bunch of data,
because each activation actually is getting a really unique range
because it's float.
Yeah, and also because like you can imagine in RNN, that same op is actually going to change its distribution based on which time step you're on, and so it really ends up being problem specific there. But you're right, for like image models, we absolutely could be doing that. So yeah, the example of represented data set is just how you would normally load data, and you just yield examples of these images. So now some numbers. So before we had released the contour quantized rewriter, which I'm not talking about in this talk because we've deprecated for a more friendly like 2.0 capable API. And but those are kind of the gold standard in quantization accuracy numbers for these image classification problems. And what we've seen is that with these changes of per channel into our quantization scheme, post-training integer quantization, which is the right column, gets pretty comparable on all these models that matter at the moment. And this is without anything fancy. So Denali's been looking into a lot of cool tricks that are figuring out how to get where the accuracy is going in post-training. So these numbers should be improving as well. But the takeaway here is that most things, 8-bit, maybe we're good enough with post-training, and only the experts really need to use quantization-aware training. So this is an example of quantization not working well is the first column, where SSD, it's the same base structure of like MobileNet, but what you're doing with your logits is a lot more. So quantizing actually introduces a lot more error here. And we see over a % drop in post-training versus quantization-aware training And this higher better is wrong. So the other two columns are new models, and no one ever went about doing quantization-aware training here because it was just too much work, and because they tried post-training. These were released after post-training was released, and post-training did really well accuracy-wise. So they just didn't bother with quantization-aware training. More models. Style transfer, we got good results in quantization, although there's not really a good metric for style transfer. The metric's like, look at it and it looks good enough. And then some speech models do really good. Everything's great. So it seems the order is a little off. So the benefit of post-training integer quantization is similar size reduction, similar speed up on CPU, and similar speed up on CPU for RNNs and convolutions, even better for convolutions because you don't have this cost. But the main thing this enables is all these integer microcontrollers, all these integer accelerators we can run on them. So here's the summary of the three tools. And the flow should usually look like you try hybrid, you see how you get on CPU. If you want to go to an accelerator or you want more in CPU, you do the post-training where you just add some representative data set. And then only as a last resort, once you see like post-training not getting good accuracy for you, try quantization-aware training. So similarly, we have tools for connection pruning, which are during training techniques. And so they have a similar API to the quantization-aware training API. And so the flow usually looks, you build your Keras model, you apply pruning, in the API you train. And often these pruning APIs are doing a lot less they're very localized to your weights. So they're not really tearing apart your graph like quantization is. And like Pulkit can attest to this, where like the pruning was like a lot simpler implementation-wise than quantization-aware training, because for quantization, you have to understand all the fusions of your backend, and whereas pruning is local to the weights. And so the flow here is you train like normal, and your resulting graph has many tensors that have lots of zeros. And right now, the flow is that you can compress your file, and it's smaller. And in the future, we're working on TensorFlow Lite runtime support for these sparse tensors and kernel support. So you'll get out of the box size reduction instead of having to do this manual compression, and you'll get speed up with.
For the sparsity in the future, when you say that it might be faster, is it in the case of structured sparsity where you force kind of block sparsity, or is it for arbitrary sparsity that it might?
So it really. So this is something where we're trying to figure out like two things, like those particular questions for given hardware, what do we want? And how do we expose this in a way that makes sense when there's like so much fragmentation for hardware. And problems. So like for certain problems, if you do arbitrary sparsity, you probably need like 99.9% sparsity to get a speed up on a particular hardware. And for CPUs and particular speech models, we've already been doing structured sparsity with certain block sizes, like you're saying. And so this training tool has the ability to set your block size. And right now we're working on, where we need to work on in the future, for a given hardware, what is the standard block size you need for that? And so you're absolutely right. There's fragmentation in two ways. It's like, will the problem allow this levels of sparsity that you desire? And is the hardware you target going to support that? So for CPU, usually we need a block. So the API here is similar to the quantization API. You provide parameters on your schedule for how you want to quantize. And here, that final sparsity is an important number. It's basically saying, at the end of training, how many values in all your weights do you want to be 0? So easy to use, just give it a try. The coverage we found is it works on a lot of models. It seems to be a very general technique. And as I said before, it works really well with quantization as well. So here's a graph that kind of confusing graph, but it's how your accuracy is affected on MobileNet, just as an example, based on how much pruning you do. And what we notice is that there's often a lot of pruning you get for free, and then there's a sudden cliff. So the goal here is for your problem to play with the parameters and figure out where is that sudden cliff, or where do you want to lie on this curve. So here we see around like 75-ish%. You're doing pretty good until then.
What technique was used to actually do the pruning?
Yeah, so here we do pruning based on the low magnitude values. So there's like a mask, and then you update that occasionally, and the mask is updated based on which values in your tensor are closest to 0. So more numbers, works great. I'll skip. And then, yeah, so in summary, quantization is hard because it is problem specific, hardware specific, and the tools have lots of trade-offs depending on which problem with which hardware. And then pruning, we're starting to get into the space of accelerating pruning. And right now they're great. It's a great technique for reducing model size, and we need to explore how that's going to look for various hardwares. How are we going to expose this in a general way? So otherwise, just any questions I can answer.
So how does like a CPU actually do the like matrix multiplication given 2 int inputs with a min and max for each?
Yeah, so the way it looks, I don't know if I have anything to look at. I can maybe just open up the code. Or, yeah, I'll try that.
It's like the min and max are
so
low.
So I'll say the words first. If it doesn't make sense, I can try to find something. So the way it actually looks at works at inference. So let's ignore 0 point for a moment because it just gets in the way. Okay, so you're say we're just doing a matrix multiplication. So your input has a certain range, which corresponds to a particular scale. Your second input, your weight, has a certain range which corresponds to a certain scale. So you have one scale, another scale, and then your output has a third independent range. So it's a third scale. So what we do is your int8 matrix multiplication actually gets accumulated into int32 values. Okay, so if you imagine that all those int32 values in the accumulator, they have an implicit scale because you just multiplied. They have an implicit scale of these two scales multiplied, right? If you wanted to recover the float value from these int32 values, you just multiply by these two scales. So this is not how it actually works, but I'm just explaining the math. So then our goal is to eventually output int8 values that lie on the output scale. So what we do in practice is we want to get from this int32 value that has implicit scale of this scale and this scale, S1 and S2, and go to S3. So we just multiply by S3 and divide by S1 and S2. So we make a new scale that's those three values, that fraction. So that's how in practice, the inference just looks like int8 times int8, int32, do this one rescale, which is this S3 over S1, S2, and then you're at your int8 value.
I see.
Does that make sense? I can, yeah.
Yeah, so you have to do like an integer division.
Yeah, and so that rescale is a floating point value, right? So, and we don't want to do that, so we do decompose that into two integers, and sometimes a shift, depending if sometimes your target only supports power of 2 scales because it just wants to implement that as a shift. So there's like that's a whole another thing where there's lots of ways to implement that rescale with trade-offs. So what TF Lite does by default is we decompose it into 2 integers and do we almost emulate float in a way.
Can I ask? I've seen equalization loss being used in training. Is that consistent with one of the? With the in training technique that you described, or is something orthogonal?
So yeah, there's a lot of techniques that we need to start including, and so right now these techniques have been these kind of end-to-end get something working type techniques where first there was no training, so we wanted quantization over training, and then. But yeah, more and more like WESD, I think you're talking. Like there's Go/WESD, where the idea is if you're given a particular min-max, what is the perfect range, perfect distribution of values such to decrease quantization error? And the answer is a uniform distribution. So WESD tries to do this by introducing a loss into your training. And yeah, these things all are compatible with when you train in the float model, but they're not offered out of the box. Because we have noticed things in some of my experiments. I noticed that WESD only works well for a particular model after you've trained for a bit, or like we still don't have like general knowledge on when exactly to use it. So we should be offering all of these, and we plan to in this toolkit as like choices for users. But yeah, that's a great technique.
Sorry, since nobody's asking, I have one more question.
Great.
You mentioned, so there's training and post-training techniques, and then also you can do it hybrid or you can do pure int. So in this quadrant, one kind of option was missing. So you showed like 3 examples, but you kind of implied that you wouldn't be doing in training quantization combined with the hybrid. Why is that?
You're absolutely right, and it's just that the tooling is not doing that right now. But that's exactly the direction we want to go. That get some metrics on what error the quantization is using, and use that to drive things like, should we be doing one or the other? Should we be doing 8 bits, or should we, for this one tensor, does it make sense to leave it in float? Does it make sense to bump it up to 16-bit? But that's absolutely right.
So there's nothing inherently wrong with it, it's just another option that you will eventually add. Okay.
Yeah, and for context like what we've added now is that if you have ops in your graph that don't support quantization, we just leave them in float. So we're already starting to get in the direction of like partial quantization, but that's exactly the direction. And what the piece that's kind of missing is these 2 information hooks, where one is, what is quantization doing to your problem task, like your error for your actual problem? We can get things like signal to noise ratio, but oftentimes that's not too representative of what's it doing to your task problem. So one thing we need is like, for this op, what is it doing to the problem? And then we can make decisions like this. And the other thing is some pluggable specification of hardware that says, for this hardware, does it even support hybrid? Because then it's not an option. But yeah, that's exactly what we need to be working on. Okay.
Oke, ini ada yang tanya ya. Saya mau tanya, saya belum terlalu paham konsep optimization ini, kayak proses konversi TensorFlow model ke TensorFlow CS nggak ya? Kan di TensorFlow CS itu dijadiin bagian kecil .bin gitu ya. Apa optimization itu juga seperti itu, dijadiin file-file terpisah gitu. Kalau hari ini kan kita baru bahas yang ini ya. Mungkin aku coba kasih lihat ya kalau yang nanti sampai ditaruh di Android gitu ya. Jadi ini kan sama nih cat and dogs gitu ya. Nah, kalau yang tadi kita buat yang udah transfer learning-nya tadi, terus kalau kita buat yang cat and dogs-nya, nah nanti kan kita nyimpen model TF Lite doang ini ya, yang habis dari optimization yang tadi. Jadi kan kalau optimization kan kayak cuman buat optimalin, dapat hasil yang paling optimal gitu loh. Terus kita pakai buat jadi model kita. Nah nanti itu kayak kita baru masukin di file Android gitu, kayak yang ini. Nah ini kita baru nanti nge-load modelnya di sini nih, Kotlin ini. Nah, nih kita load model. Tapi kita nggak akan bahas banyak yang ke Android-nya, karena kita cuman ngejelasin sampai gimana sih cara modelnya itu kita buat, terus nanti modelnya itu ditaruh di mana gitu. Nah kayak gini. Ini besok kita bahas. Gitu. Tapi kalau sampai yang kecil-kecil kayak yang di TensorFlow JS, yang kayak dibikin .bin, nggak sampai yang kayak gitu sih. Ya. Terus kalau yang tadi, yang error tadi, itu tuh ternyata aku harus upgrade dulu, harus nge-upgrade si TensorFlow tadi yang ini masih belum mau naik. Oke. Aku harus upgrade si TensorFlow dataset. Jadi kayak aku harus tambahin pip install TensorFlow-nya. Di paling atas. Aku cuma tambahin pip install upgrade si TensorFlow dataset. Terus yang split tadi itu udah nggak perlu pakai yang split all. Jadi tinggal split info tadi. Kita sambil jalan ya, bentar. Oke, ini aku kayaknya masih gemot banget ya ini jalanannya. Oke, jadi tadi yang ini benar yang atas ini udah nggak kita pakai yang dua atas. Jadi tinggal split, terus benar pakai yang ini train 80%. Terus nanti validation itu 80.290, jadi dari 80% sampai 90%. Terus yang tes itu ambil yang 90%.2 gitu. Nah, terus baru di running semua udah bisa jalan normal. Tinggal di-upgrade TensorFlow datasetnya aja. Kayak gitu. Nanti aku masukin buat yang ini ya ke Google Classroom yang udah aku benerin nanti. Jadi cuman tinggal upgrade aja karena tadi kan ini ya file direktornya nggak ditemuin, jadi harus di-upgrade dulu si TensorFlow datasetnya. Oke, kayak gitu. Ada lagi yang mau tanya mungkin? Kita tinggal TF interpreter. Ini yang tadi juga udah ada di dalam yang tadi ya. Yang tadi udah dijelasin di transfer learning. Ke part 3 mungkin kita lanjut besok karena ada jam 21.50 ternyata. Di sini masih ada lumayan banyak slide, jadi kita bisa lanjut hari Selasa. Oke, ini kan error. Sini kita pip install. Rapu-rapu ya. Rapu. Maaf, Rabu ya. Kita lanjut hari Rabu. Flow dataset. Display. Ini bukan split tapi ini log. Terus yang ini udah nggak data tapi udah bisa pakai yang cat versus log. Oke, si infonya ketinggalan. Masih error kan? Oke, kok masih error ya? Tadi aku coba di itu mau deh, udahan. Yang lain juga udah pada bisa kelas-kelas lain. Split. Into splits. Oke, ini aku nanti ulang lagi deh, coba lagi. Tadi udah bisa. Oke. Mungkin nanti ini aku ulang lagi, aku upload yang udah jadi. Iya, kok tahu-tahu nggak ngaruh ya? Karena tadi aku upgrade ngaruh. Aku coba yang tadi. Jadi masih si ininya masih error nih, masih 404. Error. Waktu install error. Astaga. Oke. Kurang S, guys. Oke. Kurang S. Pantesan harusnya tuh bisa gitu. Error. Oke. Oke, ntar ya masih loading. With validation. Split. Expected to many value to unpack. Oke lah, ini nanti aku coba lagi deh. Harusnya sih bisa. Ya, tuh split ya. Yang train itu harus, yang split di depan itu harus satu-satu ya. Nah, kalau nanti aku ubah si split di depan itu, yang bawah kan manggil si split gitu ya. Terus tadi itu waktu dicoba sama yang lain juga, splitnya tuh bisa gitu. Mungkin nanti aku coba lihat dulu yang lain deh. Harusnya sih jalan gitu. Kalau yang di contoh ini kan kayak train underscore example, validation example, test example. Kayaknya mereka tuh kalau di sini tuh kayak mau dimasukin di dalam satu doang gitu loh, split. Nah, kalau yang atas ini kan splitnya itu udah punya 3 gitu ya. Tapi nggak bisa pakai yang all. Tapi kita coba, siapa tuh bisa karena barusan. Nah, split has no attribute subsplit. Kalau mau diganti kayak itu, berarti kayak yang tadi kan nih. Bentar, ini masih. Nah, karena yang ini udah split. Many, masih sama errornya. Oke deh, nggak apa-apa. Nanti aku benerin deh yang ini errornya. Oke, karena kebetulan yang hari ini bukan modulku gitu. Oke ya, nanti aku benerin yang ini code-nya. Oke, ini udah jam 22.00. Mungkin ada yang mau bertanya dulu. Sambil ini kita masih ada yang part 3 sampai ini kurang lumayan sih, kurang 8 slide. Part 3 kita masukin di hari Rabu ya. Oke. Mungkin kalau nggak ada yang mau bertanya, ini aku ingetin lagi buat kuisnya, jangan lupa dikerjain ya, batas kuisnya besok. Oke, aku izin stop share kalau memang udah nggak ada yang tanya lagi. Oke, ya ini ya link kuisnya udah dikirim di chat. Atas kuisnya besok jam 23.45, karena dari kuisis paling malam bisanya cuma jam 23.45, nggak bisa jam 23.59 gitu. Oke, yang bisa open cam boleh open cam ya, kita dokumentasi. Oke, bentar. Oke, bentar. Aku ganti background dulu. Oke, kita mulai dari layar yang pertama ya. Oke, layar kedua. Oke. Baik, terima kasih semua yang udah hadir buat ikut kelas hari ini, materi hari ini. Nanti yang masih error mungkin aku benerin dulu, baru aku share gitu. Baik, terima kasih semuanya. Selamat malam.